The harmonious fusion of angular momentum eigenfunctions, bridging algebraic and functional representations. Prepare to embark on an intellectual odyssey as we construct a bridge uniting algebraic elegance with functional complexity. Join us as we lay the foundation by determining the pillars of the functional operator groundwork, all part of our larger quest to unravel the secrets of angular momentum eigenfunctions. How are we going to do this, you ask? Well, let's look at our problem here. We see it's composed of two parts. The first part asks us to verify or find this expression, known as equation 4.13, from the raising and lowering operators, equation 4.130, as given by the author. We also are tasked with finding this functional representation of the operator L squared, as we see as this big chunky thing, from equation 4.129, which is the LZ, and what we just proved or just verified with part A. This is all, as you see, part of a larger scheme because now we have differentials here, differentials which tell us we're operating on a function. Not just an algebraic representation where we had in a couple questions ago, where we're operating on a functional or a vector, a ket vector, so to speak. So now we get the best of both worlds. And we'll see how to do that very soon. Before we begin though, I'd like you to note that there is a PDF here that you can use to follow along, although I think in this question it's pretty easy, pretty straightforward since we know what equations to use, so just be aware, it is there for you. Stop number one along this journey is first understanding that we need to act on a test function. Since we know we have derivatives and our intricate understanding of linear momentum and that operator, we know we need to understand that we have to act on a test function as given by the hint in the question by the author. So we'll just let that equal f, but note that it is ranged over r theta phi because we're still in spherical coordinates. If you recall from, I think, last question or the question before, we had a chain rule effect that might occur, but namely product rules are what's going to happen. So let's go ahead and get everything set up for this question. Here we just have the raising operator as defined by its differentials, plus plus plus, as you see color coded. And then we have the lowering operator as described by the red negatives with its differentials. Pretty cool, pretty easy. But again, we have to act on this test function here. We could try to simplify this ahead of time, but be aware that this derivative and this derivative have to operate on everything to the right. So this bracket and this function here. That's why we have to use a test function. That's where the product rule comes from. But what we can do is try to simplify because you have an h bar and an h bar, so get that out here. The negative sign follows it, of course. And, we could factor out this e because it's to the left of any operator, so we're good there. But now we simplify to this. And what happens was we distributed this e to the right-hand side onto the right-hand side. That's why you see one here and here. And the f, we distribute it to the derivatives. So let's go ahead and now take this part here. And what we see is that when we distribute this derivative to this bracket, we get this chunky mess here. And let's go ahead and see what happens when we distribute the other one. Then we get this chunky mess here. Now is where we have to be careful in the simplification process because there's going to be a lot of moving parts. All right, as you saw with the d theta, we have to operate on the df e to the negative I term, but we know that that's a derivative with respect to theta, so e can be pushed on through since it is a function of phi. Easy enough. Similarly here, the other expression, negative I e to the negative I phi, that plops on through because of the derivative is with theta. However, the cotangent cannot, so we have a product rule here, not just a random function here. Now, on the other part where we have to distribute, now we have to be a little more careful because we have this I cotangent d phi. This operates exclusively on the e to the negative I, but also remember that the function was a function of the variables r theta phi. So although we could take a first partial with theta, we can always take another partial of that with respect to phi. So be aware, this is going to turn into a mess too. Further, when we distribute this I cotangent into this, we get two i's here, so hence the I cotangent squared. That's just a little mess that could be happening, again, with another product rule coming up. So here you see we can segment out and kind of get a narrow scope, or narrow it down to get the whole scope here. We see that after the first round of derivatives, we can simplify down because everything has an e⁻⁻⁵ in it in some form or fashion, hence the color code. This, of course, is after the chain rule, or the product rule and chain rule, hence the -I here from this derivative. And we have a double derivative, we have a double derivative, and we have a lot of simplifying to do. So, if you need to write this down, just pause the video, but let's get on with the simplifying because this is where the magic is about to happen. Okay, so we pull out that e⁻⁻⁵, and that's what's summarized here when we combine the exponent variables in the argument, because we know that multiplying two exponentials, we can just add their arguments. Now, everything else on the simplifying front needs to be handled with care. The double derivatives, or the mixed derivatives rather, of phi and theta, they cancel generously. We like that. That's awesome. In the full PDF, I have a little more about this little algebraic simplification because it can become gruesome, and you might be wondering where all these jumbling symbols are. It's in that PDF. For here, I'm just highlighting the overall scheme, and as you see, the cancellation here probably would have been hidden if we didn't use that test function, as highlighted by the author's comments. But, not too bad. I don't think this is too crazy. I think we've seen worse. Now, as we process this down with that cancellation, we can simplify that double cotangent squared gets to this point here with the -I, and then we simplify that one there. So there's just a lot of random parts that can set you off with a minus sign or some other algebraic annoyance. The other part to notice here is that when we're moving on here, we do not have any more exponentials. That's because we have two matching arguments, so that goes to e⁻⁻⁴, and then that e⁻⁻⁴ goes to 1. So that's where that comes from. The rest is just understanding what we have to look at in this particular form after we simplify it down. The square, I cosecant, the double negatives, with a partial f phi. This cotangent comes from this one. That's why the red I is squared, or the is colored red for the square. The double negative will undo itself in some form or fashion. So that's where that comes from. You bring this down, you bring that down. Now, as the color coding suggests, we have an I and a df d phi that can be factored out to their respective sides. Left factor I, right factor the partial. And what we see here is that this simplifies to what looks like a potential mess, until we remember that we could use the power of Pythagoras identities with the trig functions. And when we do this, we simplify down pretty nice. That whole thing went to just a value of 1. What a wonderful surprise. From there, now we can factor everything out that we need. As you see, everything in the function is color-coded green again. Plop that out to the right. Easy enough. And since we multiplied or operated on it to begin with, we can cancel and cancel, and we get exactly what we were trying to do. Of course, color coding the fact that the derivative natures can happen in blue, i.e. the variables theta, join them together, the variables phi, join them together, just makes it look nice. So with that, we reach our first checkpoint, which is showing or deriving the L plus L minus operators with respect to the test function and the spherical coordinates. So that's nice. As you see, we're happy now that we're halfway there. Let's not stop this momentum, no pun intended. No, I lied, very much pun intended. And continue on to part B, where we can analyze the case of L squared. All right, as indicated, this is stop number 2, and we can do this more quickly using the hint given, which is 4.112. And this equation really is what started this algebraic and not linear, but angular momentum theory off, was joining together these operators with the z in this kind of combination summarized in 4.112. It's been pivotal in this whole section, so give that equation, or put it on your equation sheet, whatever you need. It's a very vital thing to this theory. But no, enough with my ranting. What else do we know? Well, the L plus L minus, we just saw that last time. And, we just proved that. So we also know that from equation 4.129 that the functional representation in the differential sense of LZ is negative I h bar d by d phi. Okay, so then we square it here. Not that bad. Let's take a note here that this means everything has an h bar squared in it. So let's go ahead and get rid of some annoying constants. This negative, however, only affects the bracket, hence the red there. And this negative I gets squared. So then we have a negative I, that leads us to an I squared, which leads us to a -1, hence the negative there. Then we have a negative here, so that leads us to a positive there, just to make sure our signs are okay. Now, what you notice is that if I distribute this negative to everything, I get this derivative cancels with that one. And, we don't necessarily need to act on a test function in this case, since we're not looking to maneuver in such a way where we have to multiply two operators. But if you want to do this acting on a test function, feel free to continue to practice that. I think what we will notice is that this quantity cancels with this quantity regardless of what function it acts on. That's really what we're trying to say here. That being said, once we cancel them out, you notice that we still have a negative and we still have a negative, so why don't you just factor it out, which is this red here. And then you're left with this blue. But now you're left with a cotangent squared, with the d squared d phi squared, and another d phi d c squared. Oh, rambling again. But now you see we could factor out the green into this thing, and now you have a cotangent squared plus 1. But again, as ugly as this could be, and we all know the, nonsense of trig and how messy they can be with their identities, we can invoke the power of Pythagorean identity again. This is how. We know that we could go ahead and substitute in cosecant squared there. Easy enough. That makes our life simple. We also know that on this partial here, we had a cotangent, which we could write as cosine theta sine theta. And what you might remember is that cosecant was a 1 over sine. Square that bad boy, and that's how you get the 1 over sine squared. Nevertheless, what we see here is we have a second derivative and a first derivative with some kind of factor on it. This lends itself to be kind of written as a product rule if you remember from differential equations using integrating factors. Here we can just use a little hand wavy algebra to make this thing pop by factoring out a 1 over sine. When we do that, we have to put a sign here just to make sure that we're replacing what we take out. And here we're just left with a cosine. This isn't our typical product rule form, so if you switch these two in the bracket, which is fine, you see that we have cosine with the derivative plus a sine with the derivative. And this lets you know that if cosine is the derivative of the first thing, leave the second thing alone. Leave the first thing alone, take the derivative of the second thing. This is a product rule, so what we can do is factor out or rewrite the product rule in this closed form here, which is much nicer. And you notice that this is the tricks they use in the spherical Laplacians all the time, and everything that goes with the conversion to another unit system or, a coordinate system. So not too bad there, easy enough to deal with. But now that we're here, we can show that we get exactly what we were aiming to do. Not too bad. Again, the PDF has a little more in ways of the little nuance, or not really nuance, but nitpicky algebra, just because I can understand and it aggravates me when I don't see it. But, here we can see the general landscape of it, and this really was not a bad problem at all. What this is trying to do, though, is highlight or set up what is going to come next, and that's where the real fun is going to take off. That being said, thank you for watching. I really hope you enjoyed this little journey as we bridge the two forms together, because the algebraic representation was awesome, but also we know that we operate in wave functions, so we need to know that. What this tells us now is that when we look forward to what's going to happen is that we have both the angular momentum that we had from the algebraic representation from the raising lowering and this differential setup. And we see that what happens is when we set both of these terms equal to one another, we get something where we can solve for the eigenequation with the derivatives and with the L plus 1 for the L squared, the little L's as we saw it a couple questions ago, and they all tie together quite nicely. So that is the value of redefining these in terms of a functional operation or the differential operators. Pretty nice. You know, there's a lot more to this game that is being tinkered with, and the author just does a great job of laying out the landscape, and I think it's really cool to see. That being said, please consider supporting this channel by subscribing and sharing this curiosity, because clearly there's much more to come. Books, notes, and other reference materials will be found below. And if you have any questions, please feel free to reach out. Again, this stuff is fascinating, and there's a lot to uncover, and there's a lot of different ways of, sharing this material. I just think the more practice you get, the more you see it, the more you can understand its mechanisms, the better off you'll be when you're making your own connections. That being said, until next time, stay curious and happy learning.